Hello, in this video we will continue from the first video on gravity and gravitational fields and gravity and potential, and we've moved on to potential now. So that's gravitational potential and gravitational potential energy. So these are the part of the video that we'll be talking about, part of the content. Okay, that's a big title. So now we'll start talking. Let's draw a picture of the Earth. Here is a small picture of the Earth. Now, if you have an object, say here, it has a certain amount of gravitational potential energy. Okay, it can fall, and as it falls, it will convert that gravitational potential energy into kinetic energy, and the value of the gravitational potential energy it has will reduce. If the point is over here, it has further to fall towards Earth, and therefore it has got more gravitational potential energy to fall, and when it falls it will transfer that kinetic energy until it hits the Earth, etc, etc, etc. Now just imagine a point a long way over here. Okay, in fact that point is so far away, the distance between the centre of the planet and that point is in fact infinity, represented by this sidewards 8. A typical physics thing. Okay, infinity, but it's a long way away. In fact, it's so far away there is no attraction between this mass here and the mass of the planet, which we'll call big M here. None at all. It's so far away, doesn't feel any force, has no potential energy whatsoever. Okay, so therefore here we will say that the potential energy here at infinity, the potential energy, the gravitational potential energy, EP, is equal to 0. That makes a lot of sense. So therefore, if that's 0, and as you go in that direction the potential energy decreases, those values there relative to this one must be negative. So suddenly you have the idea of negative potential energies, which is a bit of a strange concept, but it's all relative to the gravitational potential energy here being 0. So as it gets closer, as it loses it and transfers it kinetic, they have to be negative values. Okay, so now that's all to do with potential energy. Now the formula for potential energy, now if it was simply, here we go, if we are on the surface, and say this is of the planet, so this is the surface, and up here we have a cliff, and on top of the cliff we have a box here, okay, and this is a distance h. We can simply say that the gravitational potential energy EP is equal to mgh. However, the difference is, of course, for the Earth, is that g is constant around the surface of the Earth. However, the gravitational field strength, which is g equals F over m, force per unit mass, which is also equal to universal constant times m divided by r squared, depends upon how far it is away, distance r away from the centre. So therefore we can't use this simple formula anymore, as we're getting a long way from the planet. So what do we do instead? So right, what we use as the formula here is, let's draw the Earth in the centre, distance r, the gravitational potential energy here, for a point mass here, the gravitational potential energy EP is simply equal to the universal gravitational constant times the mass of the planet M multiplied by the mass of the little object divided by r, and it's going to be negative because it's negative relative to the gravitational potential energy further out, which is 0, and it must lose it as it approaches the Earth. So that's a formula for the gravitational potential energy. Okay. Now, the term we were talking about in the last video was something called gravitational potential. So, and I'll put the formulas here. And the gravitational potential is defined as, so let's call that potential gravity is equal to the potential energy per unit mass. So it's equal potential energy per unit mass for a small object, and so therefore that's EP divided by M, which gives us minus G M over R, and that's the potential. Okay, right, let's do some drawing, more drawing again. So, here's the Earth, like that, and around the Earth we will have, I'll make it solid, we'll have concentric lines of equipotential. Now, they're meant to be equal around there. I'm a bit squashed. So, if we take a point here on that equipotential energy A, and a point here B, let's say that the potential at B, now it won't be, is say minus 20 joules per kilogram. It won't be, I'm just thinking about nice round numbers, minus 20 joules per kilogram. Then as we approach the Earth, the potential at A is going to be something like, it's going to be increasingly negative, larger magnitude, minus 30 joules per kilogram, until, and therefore as we go further in, that might be something like minus 50 joules per kilogram. Now I haven't drawn to scale or anything like that, and these are not revised. It just shows you that the potential becomes increasingly negative as you approach the Earth's surface. So therefore, if you had, if for instance the object were to fall from A to B, okay, the change in potential, the change in gravitational potential falls from A to B, sorry, from B to A, the difference would simply be equal to, so that's at minus 20, so the difference is 10 joules per kilogram. The potential has, if you like, become increasingly negative by 10 joules per kilogram, and that is the difference. So we'll have there, so that's change in potential. So therefore that's the change in potential. So what is, if you like, what is the loss in potential energy as it goes from B to A? Now the loss in potential energy, or change in potential energy, so that's the change in potential energy, okay, is simply equal to the change in potential Vg times the mass of the object, call this mass m, mass m, okay, which to give you that formula. Now, don't get too hung up on all the negatives. Just think about it as a change, and then if necessary, add the negatives afterwards. So clearly, the greater the mass, the greater the loss in potential energy, which makes sense, and the greater the change in potential, also the greater the, if you like, the loss in gravitational potential energy. And we'll stop there. There'll be more on this subject in the third video.